Hello everyone and welcome to the video for section 5.6 on the derivatives of the inverse trig functions. So our objectives for this particular video are number one, to develop the properties of the 6 inverse trig functions. Number two, differentiate the inverse trig functions. And number three, review of basic differentiation rules. Let's start out with a review of the inverse trig functions that we dealt with last year. In class last year, in pre-calc, we dealt with the development of 3 of the inverse trig functions: the inverse sine, arc cosine, and arc tangent. Now, when we did these things, we had to go through and set things up for the sine, cosine, tangent to be 1-to-1, so that the inverse would exist. And what we were able to do is we set this up, and we were able to define our inverse trig functions. For the inverse sine, we had a domain of -1 to 1, including those values, and the range was -pi/2 to pi/2. Remember, what happened on that is that we would only get answers that would appear or were coterminal to angles on the right side of the unit circle for the inverse sine. With the inverse cosine, again, the domain was -1 to 1, and the range was 0 to pi. So we got answers that would appear in the top half of the unit circle. Now, the nice thing about that inverse cosine is all the angles did appear actually appear on the unit circle. Whereas on the inverse sine, because we went from -pi/2 to pi/2, the negative angle possible solutions were not angles that actually appeared, but they are coterminal to the ones that are in the fourth quadrant. The inverse tangent was the domain on that was -infinity to infinity. Think about how the tangent function goes in terms of it has the vertical asymptotes and it runs all positives and negatives. And the range on that was, again, -pi/2 to pi/2, but notice in this case that -pi/2 and pi/2 were not included. And that was because the tangent function at both of those values is undefined and actually the tangent function has a vertical asymptote at -pi/2 and at pi/2. The inverse cotangent. Now we're going to get to the 3 that we did not define last year. Okay, and again, they would be similar in terms of how you set them up and the way they would be developed. The inverse cotangent was going to be the arc cotangent of x, and again, that domain on that is -infinity to infinity, which should not be a surprise when you think about the graph of the cotangent function and how similar it is to the tangent. But the one thing that happened on this one is that we would get answers that were from 0 to pi. So again, the answers to the inverse cotangent are going to be answers that do appear on the top part of the unit circle. Now we get also to the secant and cosecant. Now, one of the things you have to remember about both of those functions is that in terms of the secant and cosecant, if you remember, think about the graphs of those, we would get answers that were -1 and less. So from -infinity to -1, we could get for the secant. And then from 1 to infinity would be those. So the domain of the inverse secant is going to be the absolute value of x is greater than 1. That deals with both sides, okay? When you would get values that were from -infinity to -1, the absolute value makes that positive. Now the range on here, remember that in this case, the range is going to be from 0 to pi/2, and then from pi/2 to infinity. Notice that pi/2 is being excluded. And again, that's because at pi/2, the secant function, the actual secant function, is going to has a vertical asymptote where and so we can't actually get to, we cannot actually have an answer of pi/2. And then the arc cosecant, again, the absolute value of that has to be greater than 1. And in this case, we are able to get everything from -pi/2 to pi/2 except for 0. And again, that is because that cosecant function does have a vertical asymptote at 0. Now, one of the things we had you do last year was to go and evaluate the inverse trig function. Now, granted, we just dealt with the arc sine, arc cosine, arc tangent. If I did ask you to deal with the arc secant or arc cosecant, you probably went through and changed it, did the reciprocal, and that's probably for the most part how you're going to work with these. Now, I have, for those of you who are still in the process of getting that unit circle memorized, and I know you will have it memorized and you will be at 100% with that, by the time we take the test on this and from now on. I have included the unit circle here for us. And now when you went through the arc sine, let's take a look at how we evaluated these things. With the arc sine of square root 3 over 2, what I had to do is I have to look at this portion of the unit circle, and I wanted to find an angle that has a sine value of square root 3 over 2. Well, in this case, it's a positive, so it's going to be in the top part, and it does happen there at pi over 3. And therefore, the answer to this one would be pi over 3. When I'm looking for number 2, the arc cosine of square root 2 over 2. Now, arc cosine gives me answers in this top part here. And again, I want a positive square root 2 over 2. Well, that happens right here. That's the x-coordinate. That happens right here at pi over 4. And so the answer here would be pi over 4. The next one is the inverse tangent, the arctan of square root 3. Well, now in this case, remember, because we're looking at the arctangent, the tangent values were y over x. So I have to determine which point on this side portion of the unit circle has a tangent value of a positive square root 3. Well, I know it's got to be in the top part. And since it's y over x, I know in this case y over x needs to be square root 3. And that is going to happen if you look at the values that you have, you probably recognize that that is happening at pi over 3. And so the answer for the inverse tangent of square root 3 is going to be pi over 3. Now, number 4, the arc secant of negative 2. Well, because I'm looking at the arc secant, I know the secant is the reciprocal of cosine. And so that means that the arc secant of negative 2 here is going to be the same as an angle with the inverse cosine of negative 1/2. And so in this case, remember on the unit circle with the inverse secant, we are going to be looking at the top part. We cannot get pi over 2 as an answer because that's when the secant is undefined. But I want the arc secant to be negative 2. The negative values do occur in quadrant 2. And I know if I'm looking at an angle whose secant is negative 2, that means its cosine is negative 1/2. And so that is going to happen at the angle 2 pi over 3. And so in this case, I do get 2 pi over 3. Number 5, the arc cosecant is 0. Well, if you remember in terms of what we just saw in terms of the definition of those inverse trig functions, and if you don't have that, you can also see on page 366 of your textbook that the range of the inverse cosecant does not include 0. So in this case, right here, arc cosecant of 0, that one would be undefined. Now the arc cotangent is 0. Now remember on this one, arc cotangent is going to be, again, in this case, it is going to be an angle somewhere between 0 and pi. And I know the cotangent has to be 0. Remember, cotangent by the identities, cotangent is cosine over sine. So that means the cosine value is on top, sine value is on the bottom. And if the cotangent is 0, that means that the cosine had to be 0. And the only place that happens on this portion of the unit circle here is right here at pi over 2. So the answer on this one would be pi over 2. Next one, arc sine of negative 1/2. Now remember on this one, again, with the inverse sine, we're looking over here. Now if it's going to be negative, we know it's got to be in quadrant 4. But remember that the angles go from negative pi over 2 to pi over 2. 11 pi over 6, 7 pi over 4, 5 pi over 3, 3 pi over 2 do not fall in that range. So those are not possible answers. The arc sine of negative 1/2, I'm looking at an angle in quadrant 4 whose y-coordinate is negative 1/2. That does happen right there. But instead of 11 pi over 6, remember we would do a clockwise rotation of pi over 6 units. So the answer on that would come out to be negative pi over 6. With the arctan of negative 1, again, in terms of the tangent is negative. It's going to be negative in quadrants 2 or 4, and I know the inverse tangent gives me an angle in right over here, so our answer here has to be in quadrant 4. But like what was true with the inverse sine, we know that it's not actually the values that are labeled here, but it's going to be a negative 1. And so in this case, I'm looking arctangent. I know the tangent is the sine over cosine, or y over x, if you remember it that way. And if I'm going to get a tangent of negative 1, that means the x and y coordinates have to be exact opposites of each other. Well, where that happens is right here at 7 pi over 4. But again, because we're looking at this in terms of negative pi over 2 to pi over 2, if I start at 0 and I do that rotation, this is going to be a negative pi over 4. Arc cotangent of negative 1. Now this one right here, what happens? Again, cotangent is going to be the cosine over sine, or x over y. If it's negative, that's going to happen in either quadrants 2 or 4. But in this case, because the range of the inverse cotangent goes from 0 to pi, it is the top half, I know my answer does appear up here. I don't have to deal with any negative answers. And so in this case, where we have the relationship that will give us cotangent value of negative 1, does happen right here at 3 pi over 4. And so thus our answer here is 3 pi over 4. If you are not comfortable, if you've forgotten how to work with these inverse trig functions, don't worry, you are going to get some time to work on these and refamiliarize yourself with it. Otherwise, if you still have your notes from last year, you could take a look at those as well and kind of look over some of the problems we did, because we did a lot of stuff. This was the one where we started out when we did these. We had twist 1, twist 2, twist 3, twist 4, and at some point you guys said how many twists were we going to have. Anyway, that's what we did, and you can kind of review that. But otherwise, at this point, we need to move on. What we have here is a picture I took of off of WebAssign of the graphs of all 6 of our inverse trig functions. The first one, which you see right here, is the graph of the inverse sine. Okay, and you can see that the range is the domain is negative 1 to 1, and our range goes from negative pi over 2 to pi over 2. The second one is the inverse cosine, and you can see again the domain is negative 1 to 1, and now in this case the range is 0 to pi, and so forth. There's the graph of the inverse tangent. The inverse cotangent is right there. The inverse secant and the inverse cosecant, and you see the domain and ranges on there. The one thing I want you to recognize about these, though, is that when you look at these curves, they are smooth curves. There are no breaks. They are continuous. There's no cusp. And so therefore, there is a derivative. And so one of the things what we're going to be asking you to do is to take the derivative, find the derivative of one of these 6 inverse trig functions. And to do that, we have our derivative formulas here. So what you see in the first case here is the derivative of the inverse sine is going to be 1 over the square root of 1 minus x squared. And when we do the chain rule version, the derivative of with respect to x of the inverse sine of u is going to be u prime over the square root of 1 minus u squared. And then we have the derivative of the inverse cosine, inverse tangent, cotangent, inverse secant, inverse cosecant. And what I'd like you to do right now is pause the video and make sure you get all these written down. Now, if you want, you can just focus on these versions over here, but get these written down and then we will talk about them. Okay, at this point, I am assuming that you now have the six formulas, or the 12 versions if you want, of these things written down. And you are going to, again, you are like the other ones, you are going to have to get these memorized. You are now up to 24 derivative formulas that you are expected at this point to know. And we will show you where those are at so you can kind of make sure to refresh your memory on them in a second. But one of the things that you can use to help yourself remember these things that I did, and I hope you noticed, that the derivative of the inverse sine and the derivative of inverse cosine are very similar. And the same is true for the inverse tangent and its inverse and the inverse cotangent. And that same similarity you should have noticed for the inverse secant and the inverse cosecant. Now what you'll notice on that is that if you know the formula for the derivative of the inverse sine, inverse tangent, and inverse secant, you can also then know the derivatives of the cofunctions. The inverse cosine is going to be the opposite of the derivative of the inverse sine. The inverse derivative of the inverse cotangent is the opposite of the derivative of the inverse tangent. And that same relationship is true for the derivative of the inverse cosecant. It is the opposite of the derivative of the inverse secant. So what I'm going to do at this point is we're going to go through the proof for the derivative of the inverse sine. Okay, and you can then go and you're going to be asked to go and prove some of the other ones as well. But in terms of the proof for the derivative of the inverse sine, what we have to do on this is we're going to use the fact that y equals the inverse sine of x if and only if the sine of y equals x. Now we're going to use this to find the derivative of the inverse sine. Because what I can do with this, at this point, I am able to go and use implicit differentiation. So what I'm going to do is I am going to use this part right there, and I'm going to take the derivative with respect to x of the sine of y, and that's going to be equal to the derivative with respect to x of x. Well, the derivative of sine of y, derivative of sine is going to be cosine, so that's going to be the cosine of y times the derivative of that inside function times dy dx, and that equals the derivative of x with respect to x is going to be 1. And so when I solve this right here for dy dx, I get that dy dx is equal to 1 over the cosine of y. Now at this point you're saying, wait a second, you've just told me that the derivative of y with respect to x, where we know y is equal to the inverse sine of x. So the derivative of inverse sine of x is 1 over the cosine of y. But that's not what we saw in the previous slide. We saw that the derivative of the inverse sine was 1 over the square root of 1 minus x squared. Well, what I'm going to have to do with this is I'm going to have to go through and convert cosine of y into something involving x. And what you may remember from last year is that when we dealt with this type of thing, that we could go through and we could set up a triangle. Now again, we're going to come back to this part again here. We know the sine of y is equal to x. So I'm going to set up a triangle here. It's going to be a right triangle. And there's y. And I know since the sine of y is x, or I could say x over 1, I know by SOHCAHTOA, that tells me my opposite is x, the hypotenuse is 1. And then using the Pythagorean theorem, I can go through and find that this missing side, this other leg, is going to be equal to the square root of 1 minus x squared. And then from that, because I now have this triangle right here all labeled, I know the sides, I know that the cosine of y is equal to the adjacent side, which is going to be the square root of 1 minus x squared, over the hypotenuse, which is 1. So therefore, the cosine of y equals the square root of 1 minus x squared, which then tells us that the derivative of y with respect to x is equal to 1 over the square root of 1 minus x squared, or from that the derivative with respect to x of the arc sine of x equals 1 over the square root of 1 minus x squared. At this point, you may want to pause the video to make sure that you are totally comfortable with everything that we did. Remember on this that we started in, and the calculus that we did was in blue first, and then we used this in black to get our answer for the cosine of y, and then we made our substitution into here to get the actual derivative formula. So take a look at that. If there's something that you're not sure about, make sure to take note of that, and because you are going to be asked to do this process for some of the other trig functions. Now let's take a look at a couple examples. In the first example, we want to find the derivative of the arc sine of t squared. Well, what I'm going to do is I'm going to write down the property we know. We know that the derivative, the one we just proved, that the derivative with respect to x of the arc sine, and I'm going to use of u, is going to be u prime over the square root of 1 minus u squared. And so in this case, what I have on this one, I know u is equal to t squared, okay, and therefore, in this case, it should be dt there. This should be a t. I know that du dt, or u prime, is going to be 2t. And so, therefore, the derivative with respect to t of the arc sine of t squared is going to be 2t over the square root of 1 minus t squared squared, or I'll get 2t over the square root of 1 minus t to the fourth. Now let's look at the derivative for the inverse tangent. I know that the derivative with respect to x of the arctan of u is going to be u prime over 1 plus u squared. Well, in this case, when I look at this problem, I know u is equal to the square root of x, which would be equal to x raised to the 1/2 power. And so therefore u prime is going to be 1/2 x to the negative 1/2. And so when I work with this problem, I know that the derivative with respect to x of the arctan of the square root of x is going to be 1 over 1/2 x to the negative 1/2 all over 1 plus the square root of x, that thing squared, which will be equal to 1/2 x to the negative 1/2 all over 1 plus x. Now at this point you will be asked to either simplify it, because the book will simplify this. The numerator right up here would be 1 over 2 times the square root of x. And so when I simplify that, this is going to equal, it's going to equal 1 over 2 times the square root of x times 1 plus x. That would end up being our derivative there. Now, I think that for the most part, in terms of the book, they would probably leave it like this, but there is a possibility they could distribute it in there as well. So be aware of that as you work on these two. Last one I want to take a look at in terms of examples on this one is finding the derivative of the arc secant of 2x. Well, again, what we know on this one is you know that the derivative with respect to x of the arc secant of u is going to be u prime all over the absolute value of u times the square root of u squared minus 1. So in this particular problem, I know that u is equal to 2x, so u prime is equal to 2. And so I can say that the derivative with respect to x of the arc secant of 2x is going to be 2 over the absolute value of 2x times the square root of 2x, that quantity squared, minus 1, or that the derivative with respect to x of the arc secant of 2x is going to be, now in this case the 2's will drop off, is going to come out to be 1 over the absolute value of x times the square root of 4x squared minus 1. Now, please notice the simplification that took place there because that is going to be something you're going to want to be familiar with. Now, with these particular problems, with the derivatives, you must remember the forms that they take. You must remember where the u is, where u prime is, and how those things work from there. Also, don't be afraid to reduce the fractions once you have put things together, okay? Because there is reductions that could take place. Just make sure that you are reducing common factors and not just portions of terms as you go through that. Now at this point, in terms of the basic differentiation rules, other things that we have with this, if you look on page 371 of your textbook, page 371 has a listing of all 24 of your basic differentiation rules. So that's going to be on page 371. That's where you'll find these rules. You should go through and take a look at each one and recall them. You'll start out as just some of the basic rules we've been using that we used when we started out with the derivative. You'll also see the product rule and the quotient rule there, power rule, and so forth. Most of them are going to be in terms of the chain rule version where you have the u's, you're taking the derivative with respect to x, but it is going to be, the inside function is going to be labeled u. So you'll see that, and all 24 of these derivative rules that are on page 371, you must have committed to memory before we take the test. Now at this point, quite honestly, you should have most of them at memory already. There are a few of them that may not be as familiar, but you will want to get those familiar with yourself with those before we take the test. So with that, this does conclude this video on the inverse trig functions. We will talk a little bit more about them in class. I might do the derivation of one more, but you will also be asked to derive some of these inverse trig functions as well. So with that, I hope you have a good evening, and we will see you at our next class.